And then the second thing that can happen as a result of this, this collision between the neutron and the nucleus is a fission event. And this is where the neutron kind of smashes into the nucleus, it breaks it open, and this releases several more neutrons, which then go on to repeat a similar kind of behavior. So they move off in straight lines with their own velocity. And we also include in this kind of event the possibility of neutron capture. So that's where the neutrons absorbed into the nucleus, but no new neutrons are produced. And so based on these dynamics, we can show that the neutron or the neutron flux satisfies this equation, which is the neutron transport equation. And the way you can argue it is to say, well, I look on the left-hand side, I have the rate of change of the flux over time at some position r and velocity v. And here on the right-hand side, I have all the quantities that can contribute to this change. And so it's just a balance of neutron production and neutron loss. So first of all, we have the neutron source, which is the initial source of neutrons, but that can continue to produce neutrons throughout the process. And so we denote this by Q. Or if I look at my current configuration of neutrons, I could have had some neutron that's just sort of passed by due to transport. It's just sort of come along and passed through this configuration R and V. And this is this first term here. So it's just the neutron transport term. Or I could also have had a neutron capture or an event happen, which happens at this combined rate, sigma S and sigma F. So sigma S is the rate at which a scattering event happens, and sigma F is the rate at which a fission event happens. And so I could have had one of these events happen, and this is denoting that possibility. And if there was a scattering event, then I'm going to look at all the possible configurations that scattering event could have come from, V prime, and integrate over this. So sigma S is the rate, as I said, the rate at which this scattering event happened, and pi S is the probability that I've scattered from a velocity V prime into the current configuration that I'm interested in, V. And so I integrate over all the possibilities that a neutron could have, all the possible configurations a neutron could have had before the collision that scattered into this, this configuration. And the other possibility that could have happened, as I said, was a fission event. And this is where at rate sigma F, a fission event happened. And now I integrate over all the possible configurations that my neutrons could have had before the fission event that fission into R and V. Okay, and pi F is the average number of neutrons produced at a fission event, so it's not a probability density. Okay, so this equation says what is my current configuration, what's the flux, and how could all of these different events have contributed to that flux. Okay, and a small correction here, it should be V. Okay, so this is the neutron transport equation. It's the forwards equation, or a form of. And just to note, I'm going to keep using these operators T, S, and F in the following slides. And of course, we also have some initial and boundary conditions. So the initial condition is at time 0, I have some function g that just describes my initial configuration of neutrons. And so implicitly, my function, my flux psi depends on g throughout time as well, but I haven't indicated this. And also we have some boundary conditions that says if I'm looking at the edge of my reactor and I have a neutron here, if its velocity is pointing inwards, then the flux is 0, because I can't have neutrons come in from outside the reactor inwards to contribute to the flux later on. So I set this quantity to be 0 at the boundary for incoming neutrons. So that was the forwards equation, and that, as I said, that describes if I look at my current configuration of neutrons, where could my neutrons have come from to contribute to that configuration? And so now I want to look at the converse of that in some sense and say, well, if I have this current configuration of neutrons, where could they go to? And this is given by the backwards equation, which is the adjoint. And so first of all, I'm going to set Q, the source term, to be 0. And we do this in fissile systems because eventually, over time, the fission that comes from the collisions between neutrons and nuclei overwhelms the source term. So I'm going to set Q to be 0. And I'm going to consider the equation in an L2 space and then look at the adjoint. And we can show by just computing the adjoint of the 3 operators that I introduced earlier, that each of those adjoints is given by, sorry, V here as well. So we have the adjoint of T with the forwards arrow is now the T with the backwards arrow here. And this now has a positive here, so there's no negative here like before. And this is because if I'm looking at my current configuration, my neutron can move in a forwards direction away. Whereas before I was looking at my configuration and looking where they could have come from, so I had to kind of look backwards in time. So that was the minus there. This part stays exactly the same. And here I'm just, the adjoints just allow me to take the scatter rate and the fission rate outside of the integral. And again, this is because I'm looking at my current configuration saying where can my neutrons go to? And so at rate sigma s of RV, I can have a scatter event. And then I integrate over all the possible velocities where my neutron can go to, rather than looking at where all the configurations that I could have come from. And similarly for the fission operator. And so looking at this adjoint in the L2 space allows us to formulate the backwards neutron transport equation, which is this abstract Cauchy problem. And so phi here is the adjoint flux. And again, it's looking at the rate of change of this adjoint flux over time, but now I have the backwards operators. An initial condition, again, I just have some function G that describes the initial configuration of neutrons. And now when I look at the boundary conditions, if I have a neutron on the boundary, I need to worry about only if the velocity is pointing outwards, because if I'm on the boundary and I'm pointing outwards, I then get absorbed. So it's just a change of sign here for the boundary conditions. And it's this equation that we prefer to work with as probabilists, because we can say, okay, if I look at an initial configuration of particles, where can my process go to? How do I describe the dynamics forwards in time, even though it's called the backwards equation? And what we're interested in is looking at the leading order behavior of this backwards equation. And this involves finding the leading eigentriple. So I want to find alpha, a real number, and 2 functions, phi and phi tilde, which are so phi is the right eigenfunction with respect to the leading eigenvalue alpha, and phi tilde is the left eigenfunction with respect to the same eigenvalue. And the reason one of the reasons we're interested in this is because this describes the long-term behavior of our system. And so we have these 3 classifications, like in branching processes, that say if alpha is negative, my system is subcritical, so eventually it will die out. If it's strictly positive, the system is supercritical, so we have an exponential growth of the number of particles. And if alpha is equal to 0, the system's critical. And so there's this balance between neutron production and neutron absorption. But there are some problems with this from a simulation perspective. So first of all, we posed the abstract Cauchy problem in L2, which means that these functions phi and phi tilde are in L2. And if we want to try to do Monte Carlo simulations, what we really want to do is use any bounded function. We want to use indicators that the process is lying in a certain area, or just constant functions. But we can't do this based on the current formulation of the problem. And also, it can become very complicated to simulate these systems. So as you can imagine, you have lots and lots of particles that have been produced. And so to track all of these particles becomes quite complicated. And so to just give an idea of how complicated this can be, we have some models of nuclear reactors. And so here, the different colors represent different materials, and each of these materials has different properties. So different scatter rates, different fission rates, and different values for the density in each material. And again, another reactor, you end up having to track lots and lots and lots of particles and keeping track of the different behaviors through these different materials. So we want to try to find a more efficient way of doing that. And the question is, can we use probabilistic methods to do that? And here's an example of some of the cross sections. So this is an example of the fission cross section in different materials. So they can become very irregular and very, very nasty. And so I think a few years ago, when Answers posed this problem at the workshop at Bath, Andreas got very, very happy because he noticed a branching process. And so he's like, okay, can we model this using branching processes, and can we use the theory of branching processes to try to inform more efficient simulations? So now I'm going to define the branching process that we will use to model this system of neutrons. So first, just to fix some notation, we're going to have D is a non-empty bounded open subset of R3, which is going to be the spatial reactor. And we're going to take the velocity space to be some three-dimensional annulus. So there's a minimum velocity and a maximum velocity. And I'll let NT be the number of particles that are going to be alive at time t, and their configurations will be denoted by RIT and VIT, which is the position and velocity of the ith velocity at time t. And so I'm just going to build this branching process based exactly on the dynamics that I described earlier, based on the real system. So again, suppose we start with a neutron, a particle with configuration R and V, so spatial position R and velocity V. Then it will just move in a straight line according to this velocity until one of three things occur. So the neutron hits the boundary of D, at which point it's absorbed and it's killed, and we don't take it into consideration anymore. It's removed from the system. Or at some random time TS, which has this distribution, a neutron will scatter. And this is given by the rate sigma s. And then its new velocity will be chosen according to the density that I introduced before, the probability density pi s. So it says this gives the probability of having a new velocity v prime, say, given that there was a scattering rate at position r plus vs with velocity v. And similarly, at some random time tf, there could be a fission event, which has this distribution. So the same kind of thing, but now with rate sigma f. And when this happens, a random number n of neutrons is produced and each of these neutrons is created at the same position, the same spatial position as the fission event, but they now have new velocities v prime. And we let the point process ZP describe this new configuration of neutrons at a fission event. So if you like, Z is given by the sum of Diracs at each of these velocities v I. And in order to match the behavior of the neutron transport equation, I'm going to ask that the average of this point process Z is given by the density pi f, so that this really does describe, so pi f does describe the average number of neutrons produced with velocity v prime. And based on these dynamics, we can formally represent the branching process by these atomic measures, so xt, and all I do is I take a unit mass and I place it at each of the configurations for each of the neutrons and then add them all up. And this is my branching process. And what I want to do now is look at the average behavior of the system. And so I define the expectation semigroup, which is the average of my system of neutrons under the action of some function g at time t when I've started from an initial neutron with configuration R and V. So what it means is I just take the function applied to each of the neutrons, add them all up, and take the average and look at the average of the system conditioned on the fact that I started with one neutron. And just note that based on the dynamics that I described previously, we have the flux is equal to 0 at the boundary for outgoing neutrons, because I said that if a neutron hits the boundary, it's killed. And at time 0, we have that the flux, or the expectation semigroup says that at time 0, the configuration of neutrons is described by the function g. So we can already see that the expectation semigroup that I've described here matches the initial boundary conditions of the flux of the system of the real physical system. And so we want to understand in what sense does this average behavior of the branching process really match up with the flux of the real life system. So first introduce two hypotheses. So the first is that the cross sections, so the scatter rates, fission rates, and densities are usually uniformly bounded from above. And this is just to ensure that I can't have activity, scattering, and fission happening infinitely fast, just to make sure that the system is nicely behaved. And then I also ask that the infimum of this quantity is strictly positive. And this is just to ensure that there's a minimal activity everywhere, so that I don't get trapped somewhere forever. And under these two conditions, I can show that the expectation semigroup that I defined on the previous slide satisfies this equation. And of course, it's a little bit different to the neutron transport equation, the backwards equation that I defined earlier, but there are similarities. So first of all, we can see that this describes the transport term. So my particle, if I start with a single particle at RV, it could have just traveled in a straight line until time t and nothing happened. Or at some rate, I could have had some event, which is given by the total sigma s plus sigma f. And if it was a scattering event, which occurs at rate sigma s, then I can put down a new particle with velocity v prime that's chosen according to the probability density function pi s. And similarly for a fission event at some rate, at the rate sigma f, there was a fission event, and I put down some number of neutrons, which is described by the density function pi f. However, because of the irregularity of the gradient operator that appeared in the neutron transport equation on the first few slides, if we want to work with just general bounded functions, we can't actually look at the gradient of these functions. And so what we do instead is look at the mild form of the equation, which is the integral form, to say, well, this is our view of the neutron transport equation. This is our probabilistic view. But of course, we still want to show that there is a relation between the two, that, yeah, okay, the equations may look similar, but also different. So what is the link between the two? And under the conditions that I gave on the previous slide, we can show that the mild solution, the expectation semigroup, is equal to the flux on L2. So if I take L2 functions and look at the inner product between F and my semigroup applied to G, then we can show that it's equal to the adjoint flux, which was the flux that appeared in the backwards equation, and that this is dual still to the forwards equation. So that there really is a link between the average behavior of the branching process and the flux that we described in the first two equations. But the point of using this expectation semigroup, as I said, it allows us to use a much larger class of functions to try to now use this branching process to simulate, to make simulations, to estimate certain quantities. In one of the previous slides, I said we were interested in looking at the leading eigentriple to look at the leading order behavior. So now we need to work out what this looks like from the point of view from the branching process. What does it mean to have a leading eigentriple? And with Andres and Denis Villemont, we have this result that says under the assumptions H1 and H2, for the branching process, we do indeed have the existence of a leading eigenvalue, lambda star, which was alpha as I described before, and two positive bounded functions, phi and phi tilde, which are the right and left eigenfunctions for the linear semigroup respectively. So here we can see that phi tilde is the left eigenfunction with respect to the eigenvalue lambda star, and phi is the right eigenfunction with respect to the same eigenvalue. So these quantities exist even for this sort of extended system for this for the branching process. And we can also show that we have convergence of the linear semigroup towards the stationary distribution. So if I normalize by this e to the minus lambda star t and phi tilde, then this converges towards the left eigenfunction exponentially quickly. And what this means is that lambda star describes the average growth of the number of particles in the system. And phi and phi tilde tell me where in the reactor I've got more activity happening. So where my branching happens more often or more quickly, and where I've got more absorption. So it really tells me quite a lot about the reactor. And so I know that if I do some renormalization, then the system will converge towards this stationary distribution. And it's just nice to see that this result is actually uniform in all starting positions, all test functions G, and for all time t. So we don't even have to worry about taking particular starting positions, particular initial measures, certain functions or anything like that. And so from this result, as I said, we can show that the linear semigroup behaves like this leading order term, e to the lambda star t, with the growth of the system, and then a combination of the left and right eigenfunctions. So what does this mean from the point of view of simulations? So if we do some manipulation of this asymptotic, we can look at the log of the average number of particles in the system at time t, divide by t, and let t go to infinity, and this will tell us what lambda star is. And so for simulations, this means that we can approximate this by 1 over some large time t, log of some average. So if I simulate my system n capital N times for n large, so take the empirical average of the number of particles, take the log, and then divide by this big time t, I'm going to get an approximation for the leading eigenvalue lambda star. And then to compute the left and right eigenfunctions, we can look at the occupation measure. So if I look at the linear semigroup, the average of my system, and normalize by the growth term, and look at its occupation between 0 and t, and divide by t, and take t to infinity, then I get this term on the left. And what this means is that if I fix an initial position, say r and v, and then I take different test functions g, I can start to build a profile of this inner product as g varies. So I can start to build a profile of phi tilde. And in particular, if I take g to be the indicator that I'm in some tiny box, d0, v0, then I can start to build a histogram by looking at the occupation in each of these pixels to build up an idea of what phi tilde looks like. And then conversely, if I fix a test function g, then I can vary my initial configurations r and v and compute this quantity for each of these initial configurations to get an idea of what phi looks like. And so I'm going to briefly show a toy model. I'm not going to go into the details of the Monte Carlo simulations. I think Alex and Min will talk about that, but we have we built a little toy model that was based on a square reactor with 4 circles, which are representing fissile rods that had much higher activity in these rods and higher absorption outside. And then we just ran the branching process and tried to see if we could get sensible things out for estimating lambda star, phi, and phi tilde. And so we computed an estimate of lambda star. So this is lambda star, and this is time t, using the formula that I showed on the previous slide. And we can see that it starts to converge. Of course, this doesn't really say much because the system that I built, or that we built, is too complicated to solve analytically. So we can't say, oh yes, this is the true eigenvalue, but it gives some idea that we can get a convergent, something that converges to what we hope is the growth of the system. And similarly, we use the occupation measure to build an idea of what phi and phi tilde should look like. And we can see that it's starting to pick out these circles as having higher activity. So the red means that my value of phi tilde is much higher in these areas. And so it really is describing where in my reactor I've got more fission and where I'm more likely to survive. But we haven't said anything new. We've just said, here's a branching process. We can formally define it and show that it's related to the flux and use it to simulate the system, which is exactly what everyone's been doing for years. So this is not saying anything new. So what can we offer as probabilists from the branching processes perspective that really offers something a bit different? And so now I'm going to talk about a single particle representation of the branching process, which is often called the many-to-one or Feynman-Catch formula. And so for the moment, I'm just going to forget about the branching process that I defined. And I'm going to introduce a new process called the neutron random walk. And this is given by the couple R and epsilon, where R is the position of a single particle at time t, and epsilon t is its velocity. And it moves around in the same space in the reactor with the same velocity space. And it moves from an initial configuration R and V, and still moves in a straight line until it either hits the edge of the reactor, in which case it's killed as before, or it scatters. And this time, instead of scattering at rate sigma s, it scatters at rate alpha. And I'll define alpha properly later, but let's just say it's some rate alpha that tells me how this process scatters. And when it does so, I have a different probability density from pi s, which I'll call pi. And this tells me how to choose my new velocity when there's a scattering event. And so I just have a single particle that's scattering around the domain until it gets killed on the boundary. So there's no fission in this. And I want to describe a semigroup associated to the neutron random walk by phi t of g. And this is the average of the neutron random walk under the action of some function g. But I also add an extra weight, an exponential weighting factor here that's given by some bounded function beta. And again, I'll define that later. Okay, so now I'm interested in this semigroup and the average behavior of this particle, but weighted by the exponential factor. And we can show that the evolution equation for this semigroup is given here. So again, up to time t, nothing could have happened. I could have just moved in a straight line. Or there was a scattering event at rate alpha. And when there is, I choose a new velocity according to the probability density pi. And then I have this extra term here, beta, which is coming from the potential here. So we can see it does look a bit like the neutron transport equation, at least the mild version of the neutron transport equation that I defined for the branching process. And what we want to look at is what values of alpha, beta, and pi will make this equation the same as that. So then the average behavior of this single particle, this weighted particle, matches the average behavior of the branching process. And it turns out that these three, these definitions of alpha, pi, and beta are the correct ones to choose. So what this means is that the rate alpha should be equal to the total rate of something happening in the branching process. So whenever there's a scatter or whenever there's a fission for any of I take the total mass or the average of the fission event, the branching event. And so this should describe the rate at which anything happens in the branching process. And for the density, this is described by a mix of the scattering density and the fission density. But it's normalized by this quantity alpha, this rate alpha, to make it a probability density. And then beta is given by the fission rate times the mean mass produced at a branching event minus 1. And I'll describe what this corresponds to in a picture on the next slide. But for these definitions of alpha, pi, and beta, we can show that the linear semigroup phi t of the neutron random walk is also a solution to the neutron transport equation. And so the average behavior of the branching process is the same as the average behavior of this weighted particle. So I said I would draw a picture. So imagine if this is the branching process at some time t, how the neutron random walk behaves is to say, okay, I'll start at the same position and I'll move in a straight line and I'll follow exactly the transport term of the process. But when there's a scatter in the branching process, the neutron random walk will also scatter because of this sigma s term here. And so then it continues and continues. And then there's a fission event in the branching process. And in this case, this also corresponds to a scatter in the neutron random walk because of this term here, because of the sigma Fm. And when it does, it will choose one of the neutrons produced uniformly, say this one, to follow, and then it will continue to follow this path. But in order to compensate for the fact that the branching process has lots of particles and this single particle doesn't, this is where the potential term beta comes in. So the beta adds the weight of the extra particles that I didn't take into account here. So this is why it's m-1 because I've used one of the particles to follow for the neutron random walk. And then I'll use the extra particles and the extra mass to create the weight, the exponential weighting factor, so that really the average masses of the system are the same and the average behaviors of the two systems are the same. And so now, because we know that the average behavior of these two systems are the same, we can go back to the Penn-Frobenius result and say, well, actually, this also applies to the Feynman-Catch formula, to the neutron random walk. And the leading order behavior of this neutron random walk with the potential is also given by the same leading order behavior as the branching process. And so we can do exactly the same thing here, but instead of the number of particles to estimate the leading eigenvalue, I can use the mass, the exponential weighting factor, to estimate lambda star. And here I can look at the average behavior of the particles, of the single particle, and look at its occupation measure as opposed to the branching process. And so already this, or naively at least, this seems better because now we have one single particle that can tell us exactly the same information as the entire branching process, at least on average. So instead of simulating this entire tree of particles, we can just simulate this single particle lots of times and look at its average behavior and estimate lambda star, phi and phi tilde. But of course, again, we ran into problems when we looked at this, because in order to get the same information as the branching process from this single particle system, you need to simulate lots and lots and lots and lots and lots of single particles, of lots of neutron random walks. And also because it's just a single trajectory, a lot of the time the trajectory won't explore much of the space. It will just exit the domain and be killed on the boundary fairly quickly. And so you end up wasting lots of simulations that don't tell you very much about the system. So that was our first idea, which turned out not to be brilliant. But is there something else that we can do now? Is there some way we can improve this single particle behavior? And so what we did was to look at the average behavior of the system, but under the action of the right eigenfunction phi. And we know that this is a right eigenfunction. So if I apply phi to my system at time t, I've just got the growth of the system times phi of the initial position. And so if I normalize by this term on each side, that means the expectation with the normalization is equal to 1. And so these two quantities are martingales. And I'm going to worry about the first one in the next part of the talk, and I'm going to focus on this one. And I want to know what this martingale can tell us about the neutron random walk. If I do some form of transformation associated to this quantity here, can I improve the neutron random walk in some way? And so I'm going to define a change of measure according to this martingale. And all this means is that I take my neutron random walk and I look at it through a different pair of glasses. So I modify its behavior a little bit according to this term. And what I want to know what this new pair of glasses, what this change of measure tells me about the process, what the behavior of this single particle system looks like now. So I'm just going to introduce A third hypothesis, which is that the fission offspring is bounded by some maximum constant n max. And this is not restrictive because, you know, there are only a finite number of neutrons in the universe, if you like, so this is fine. This is realistic, at least. And under the two assumptions that I defined before and this third one, we can show that if I take my neutron random walk under this new measure, so with my new pair of glasses, that this is also a neutron random walk, but with a different scatter rate and a different probability density when I scatter. And what the change of measure does is that when the neutron is heading towards an area in the domain where it's going to be killed, when it's getting towards a boundary, for example, or it's getting to an area where there's a lot of absorption, the new scatter rate here will tell the particle that there's danger coming, it's going to die, so it needs to scatter very, very quickly. It speeds up the rate of scatter to sort of make sure it gets out of danger, if you like. And then when it has scattered, this new density tells the particle to move into new directions where the new velocity is favorable compared to the velocity in which it was already going in. So if this new velocity gives a better value of phi than the old velocity, it will tell the particle that it should go in this direction in order to stay alive. And this means that you get a particle under this new law that is conservative. It stays alive, and it has stationary distribution given by the product of the two, which is great, which means that we don't end up losing, wasting simulations by simulating a single particle that gets killed all the time. We've got a single particle that is forced away from areas where it's going to kill and stays alive. But of course, there are problems with this as well. So what we wanted to try to simulate was, or to estimate was, lambda star, phi, and phi tilde. But in order to define this change of measure, to get this particle that is great and that's going to give us all the answers, I need to know phi and lambda star. And so this is one of the challenges that that is currently being looked at by Alex, Andreas, that Minmin's also looked at, Simon as well, and that they also have another PhD student, Tom Davis, who's looking at as well, to try to come up with ways that we can try to work with some form of biasing, but that doesn't require knowledge of phi and lambda star in the first place. So just some current open questions or current research or future research directions. Are there some other biasing techniques that we can use, as I said, that isn't necessarily based on phi, but some other function that maybe looks like phi? Can we use some properties that we know about phi to build some other functions? Can we use sequential Monte Carlo, so population control methods to try to simulate this system? And then also to look at complexity analysis and stability analysis of this system as well. And another question as well that is of interest is a multi-type system. So actually, when you look at these systems, it's not just neutrons that are involved. You have alpha particles, beta particles, gamma. There's also something called delayed neutrons, and this is where after a fission event, as well as neutrons being released immediately, you have some neutrons that are held in the same place and then released later on. And this gives a bigger picture of what's going on, a more complete picture. So can we try to analyze this system with the different particle behaviors as well? And so we started to look at this from an analytical perspective, at least at the start of my PhD. And so this is something that we need to look at as well from the probabilistic perspective. Thank you.
Okay. Okay, so you've got actually you've got 9 to 10 and 10:30 to 11:30. So we take a half-hour break. But before that, I would like to ask if there are any questions from the audience. Now, my experience with Zoom is that it takes a minute or so for people to kind of get on and write questions or come onto the mic. So I will, in contrast to the way we do it live, where the chair kind of asks the last question, I'll ask the first question. So if you go all the way back to the beginning, I mean, you've got quite a few slides there, 49. So if you whiz back to where you wrote the mild equation.
Yeah. Okay. There we go.
So you kind of didn't write this with semi-groups, which made me a little bit sad because I thought it was quite pretty. Could you write that out in semi-group form, just because there's something I think that's worth pointing out. So what Emma's going to do is this long, complicated thing she's going to write in terms of there's something here UT, which we'll see in a minute, but also the operators that she defined earlier.
Well, I define the operators a little bit differently so that the transport operator that you use is slightly different, but it's okay.
Okay. So this equation, the reason why I've kind of asked Emma to do this is because for those of you who are familiar with spatial branching processes, now I know some of you are familiar with branching Brownian motion, some of you are go all the way into super processes, some of you go all the way into fragmentation processes. So UT is literally what you see right underneath it. It's the shift of space by VT. That's essentially what UT is doing. It's just moving the particle from R to R plus VT. And S and F are two operators which correspond to these integral terms with the pi S and the pi F. So this is exactly how we write evolution equations, mean semi-group evolution equations of every branching process that we know on the planet. So whether you like super processes, whether you like fragmentation processes, whether you like branching Brownian motion, they all conform, they all have a version of their mean semi-group which takes this form. So that the psi-t is the mean semi-group, the UT is essentially a movement operator, which for branching Brownian motion would be the semi-group of Brownian motion. So UT would be where a Brownian motion particle gets when starting at, we would replace RV by its starting position X. So where does it get to by time t? S and F would be the mean, would be the combined, slightly talking a bit of bullshit here. It's the replacement of UT and the S term in the integral. If we combine those two together, that would be what we replace by Brownian motion in a BBM. And the F term is the mean mass creation, if you like, in a branching process. So also for the BBM fans out there, the other way to think of this mild equation is if you differentiate it in time, then the semi-group will differentiate to an operator, which in the BBM setting would be the Laplacian. And then the term with the F here is going to give you your mean mass creation. This equation is very familiar for those of you who know super processes. This is exactly how Dynkin like to describe the evolution of super processes. And for the fragmentation people out there, this is also, I think, how you describe the evolution of mean semi-groups for fragmentation. So in a sense, although the notation is very heavy, it very much, it's extremely well aligned with classical branching process representation if you just stand back at the right distance and squint at it. Right, I'm going to shut up now. And that wasn't a question, that was a comment. I think somebody's got their hand up. So it's Tony. Do you want to just take the mic and put your camera on if you want? Or just speak into the mic?
Thanks. Yes, thank you. Thank you, Emma, for this nice introduction. So I had a question about the last part.
Okay.
So if you go back to page maybe 30, where you go from, you know, this many particle branching to a single one with weights.
Okay. Yeah.
So I think at that point you said, okay, it's a nice idea on the paper, but when I use it in practice, I have difficulties because I don't know. You said I think I need to make many instances of this process to get something reasonable. So I wanted to understand this better, and also I wanted to understand why the cure you propose, which is to introduce actually the phi and phi tilde, the left and right eigenvectors, could be, how can this be made practical? Because of course you don't know these guys, you are looking for them. So what do you have in mind to make it, I mean, to solve your numerical question?
So for the first question, the idea is that because it's just a single particle as opposed to a branching process, you could have some particles that maybe just explore a very tiny bit of the reactor and then get killed because they hit the boundary. And so they don't really tell you much information, but you still had to use computation time to simulate these. So it's kind of a waste of time in some sense. And you could have lots of these and not very many trajectories that explore the space properly to give you the right information that you need.
Okay, but this would also be a problem with the naive branching process that you could use. I mean, in some sense, it's just, no?
Yeah, of course. Yeah, I mean, you could still have that happen, but I think you'd probably require less copies of the branching process. But of course, this is not the same as the number of copies of the neutron under walk. But yeah, no, of course. And for the second question, I don't want to give too much away because I think Min and Alex will talk about this in the future talks. But the idea is roughly to say, okay, well, we know that phi is probably going to be 0 on the boundary. And if you have certain areas of high absorption. And the idea with phi is to try to reflect it away from these areas. So can we build a function h that has this same behavior, but has a bit more freedom with the space in between to try to introduce a different change of measure?
I see. Okay, thanks.
Thanks.
Okay, any more questions there? I think, Andy, you've got your hand up. Do you want to just take the mic?
Mic is off.
You're muted.
No, he's unmuted now. He's definitely unmuted. The little thing says unmuted.
You can't hear me now.
Are you plugged in? Sorry, Andy. You want to have a fiddle, Andy, and I'll see if anyone
Or you
else
could put your question in the chat.
Okay, write it. There you go, Tony. Just while you're writing it, I'll add to Tony's question, which is really the whole crux of the whole story. Really, is I'm glad we've got a chance to discuss. We've got a discussion session, and I really.
Hello.
Oh, hi, Andy. Do you want to?
Oh, is that working now?
That's working, yeah.
Amazing. Sorry to cut you off. Yeah, so the question I had, it was something quite near the start when you had this kind of curly Z object and curly E object. I forget which slide it was.
Yep. I don't remember. It was the branching process.
Yeah, that's right.
There we go.
Yeah, here we go. Am I right in thinking, so here what you've basically specified at the bottom is a kind of moment matching condition. Is that right? But you've not actually defined the law of these particles. Is that right? Or have I missed
said
something?
that Z is the point process that describes exactly the number of particles and the velocities that are produced at fission. And P is its law. And then I want to specify that in order to match the average behavior that's given by the neutron transport equation, that this point process, that's the sort of abstract object, does match up with the average that's given by pi f.
But is that specifying a law, or is that just like a moment condition? Do you see
Yeah,
what
so
I'm asking?
I mean, I've specified the law here. Z and P is exactly the law of the offspring distribution.
Right. Okay. Okay.
Of course, so if you were to just look at the system with pi f, for example, and say I just want to match this average behavior, then it's saying you could of course build lots of different examples of Z and P that do match this average behavior. Yeah.
And so you have to choose one, I guess, or it doesn't matter?
Yeah, you can just, I think so, yeah. I guess yeah, we've not really looked at matching this up to the real system with specifics of the point process and so on.
Okay, thank you.
This is actually where there's some, it'd be nice if occasionally some more nuclear guys pipe in, because I know that they do branching simulations and they kind of make their own distribution up. And I don't think they ever go farther than 2 or 3 neutrons per fission.
I think what normally happens is the expected offspring and say it's 2.4, then you would flip a coin and either have 2 or 3 offspring. I believe that's what tends to happen. I'm not sure experimentally how easy it is to get actual offspring distributions in the sense you might want it here. Because I mean, if you do an experiment, I mean, maybe some of the others would know better, but if you do an experiment, you can perhaps see the multiplication factors, but it might be harder to, maybe physicists do know, but.
If I might add a comment on this, so it's Eric Dumonteil. Indeed, usually we are only sampling fission events so that we conserve mean quantities. For example, 2.4 for the mean number of neutrons produced by a neutron fission at thermal energies. But the past years, there have been developments in Monte Carlo codes called analog functionalities, and where we sampled all, let's say, generating function of the number of neutrons produced by a fission. So one of the challenges is that we first need to have proper measurements of those quantities, and then we have to include them in the codes, but that has been done, and it's mainly used to study the stochastic neutron noise, for example, near research reactors or zero power reactors.
Thanks, Eric. So just for everybody, Eric works at the CEA, the CEA in French, the French National Nuclear Atomic. Is that right? The Nuclear Atomic Agency, I suppose I would translate it.
Yeah, that's great.
Yep, and we've also had a comment from Andrea Zoya, who's also at the same institution, who says the distribution has been experimentally measured, but in simulations, typically only the average is preserved. And there's a question here from Jeff Dobson, who is from Answers, who sponsored Emma's PhD, just to give them another plug. So he says, I wonder if for subcritical systems, you could reintroduce the fixed source term Q. So more generally, what happens if you put Q? What happens to all this stuff if you put Q back in?
So yeah, you can add Q back in, and your Feynman catch formula will have this extra term that accounts for integrating over Q against the single particle term as well. So you can still do all of this with a source term in if you want to, yeah.
So the take-home message seems to be that you've taken this Neutron transport equation, flipped it into the dual space, and then said, I don't like that. I want a Feynman catch representation because that makes me more comfortable for averages and simulations. And you've said, well, I can average a branching process, or I could also average any other stochastic process that, so long as it fits the same evolution. And this is very much Andy's question. The mean of the system is not sufficient to uniquely pin down the stochastic process underneath it. So there are actually many representations, potential representations of a Feynman catch nature that we could pin in there. And so your point, Emma, is that whereas a branching is one representation and many to one is another, and the question is which of these is better for simulation questions. Right, Zhenya, you've got a question there. Do you want to go to Mike?
Hi, Andrew.
Hi,
yeah, I have a question. I have a question actually related to what you guys are talking about right now. So if you take two branching process and they have the different offspring law, but their offspring law have the same mean, does that really influence anything on the eigen behavior, eigenfunction, and the eigenvalue? Why I think it doesn't influence anything.
No, because you're just looking at the average behavior of your system. And so if your average growth is still the
same. So they are all the same. Okay, I just want to be.
I think if you change spatially where you're having your offspring, then this could change the eigenfunction. This is a conjecture, but this is how I see it. But this wouldn't change the eigenvalue if your mean growth was still the same. But if you were to say, because of sort of my heuristic, at least, interpretation of the eigenfunctions being where in your reactor the fission, the absorption is, if you were to really change the spatial distribution of your offspring distribution, then possibly this could change the firefighting.
Yeah, if you don't change the distribution of the mean according to the space, maybe nothing will be.
That's right. That's right. The eigen triple belongs to the evolution, the mean evolution. So long as what you choose for your stochastic process maps into that mean evolution, you'll see the same triple. Okay, it's quarter. I don't think there's. Let me just double check. I don't think there's anything else in the chat. So it's